Welcome. This is our second video in the series on PCB layout-driven design with VSS. In this video, we'll take a look at component modeling, which is step one of a multi-step process that will allow us to simulate at the VSS level, or the system simulation level, our board-level interconnects in addition to the components on the board. In this step, we'll show how we do the component modeling. We'll include an approach to modeling not only Ballon switches and power amplifiers, but other devices as well. Our approach will focus on developing models in Microwave Office, and then we'll insert those models into VSS using the LinS model, or simulation-based linear model, for linear components in Microwave Office, or the NLS, which is a nonlinear simulation-based component, which actually takes and constructs a behavioral model from Microwave Office into VSS. Here I'm showing an antenna structure. This antenna structure has been designed using Axiom, the Microwave Office EM solver that's very fast and highly accurate. I can lay out the antenna structure exactly as I would like to see it on the board and reuse this layout for the board as well as for the EM simulation. The results I get from the EM simulation will be S parameters, and those can be inserted directly into our VSS simulation using the LinS block. Where we have S parameters from a manufacturer, here I'm showing a Johansson Ballon that I want to use on my board, and the manufacturer has provided S parameters for us for how this component should work. We can include them directly in our VSS simulation, again by using a LinS block. However, in this case, instead of them being a EM structure, as for our antenna, they're a data file in our Microwave Office project in the AWR Design Environment project tray. We can develop our own behavioral models by understanding how certain components work. Here I'm modeling a diversity switch in a very ideal way by using two SPDT elements, or single pole double throw switch elements, to provide the functionality for the diversity switch. Of course, in this implementation, I don't have any datasheet type functionality like isolation or insertion loss. You'll notice that I'm using many ports on here, and this is to map directly to the number of pins on this component. So while the performance or simulation of this, which would be included in VSS as a LinS block, is very ideal, in other words, the ports are pretty much just short-circuited to each other, I'm able to represent the number of pins on the package so that when I go to the layout, I can take into account all the extra layout that will be necessary in terms of pad stacks and any interconnects for control voltages and that sort of thing. I can take that into account directly by making sure I have enough pins on my symbol, and that'll correspond to the pins on the package. I can go one step deeper and actually develop a behavioral model for a switch. Here I'm showing a TR switch that I've modeled based on a datasheet from MACOM, and by using the isolator symbol and using the splitter elements, I can model the insertion loss from one path to another. I'm sorry, from the input to the output, and I can also model the isolation of one path to another. And this is all done by matching up the performance of my model here using this sort of behavioral structure, behavioral hierarchical schematic to the datasheet performance specifications. And again, all the elements I've shown so far would map to a LinS, or simulation-based linear model, into VSS. I can model them in Microwave Office. I can do S parameter measurements in Microwave Office. I can see that it's matching the datasheet, and then I can embed that directly into the VSS simulation and have it perform at the system level the very same way it performs in Microwave Office, but again in a system simulation like EVM or bit error rate or ACPR. To model some of the nonlinear elements, we want to do something a little bit more complex. And what I've done is I've chosen a Anadigix power amplifier that's specifically been designed for WiMAX applications. And what I did was I took the data sheet, which has information about its nonlinear characteristics like P1 dB and power output, and gain and EVM, and I've put the spec sheet information that was available directly onto this NLAMP model in Microwave Office. Now that's going to give me the nonlinearity in terms of voltage in and voltage out, or power in and power out capability, but it's going to be sort of independent of frequency. Well, also on the Anadigix data sheet is some frequency information, and I've been able to capture that with a low-pass filter right here. So by tuning the characteristics of the low-pass filter and looking at my behavioral model model in a linear or S parameter measurement, I'm able to get the frequency shape. And when I combine the frequency characteristics with the nonlinear amplifier characteristics, I get a frequency and power relationship that sort of superimposed or superposition in those two different domains of power and frequency. And that gives me a very, very representative or very accurate behavioral type model of what the Anadigix power amplifier is capable of doing. Now, to go one step further, if I have information about output impedance, I can capture some of that with one of the many elements in Microwave Office that are able to vary the impedance or the match presented to a port, and I've chosen to do that with the HB tuner right here. Now, the result of all this, if I go ahead and look at EVM, is I get an EVM curve like this swept over input power to my power amplifier, and with just a very simple model, I was able to reproduce the EVM curve that is on the Anadigix datasheet. So now I have a power amplifier, a very nonlinear element that's ready to go into my board design that I'm able to do in Microwave Office. But furthermore, I can take all of these components or the board as a whole and insert it into my WiMAX EVM measurement inside of VSS, and I'm going to be able to simulate any one component to see how it affects some of these system level measurements, or I can cascade them all together without any interconnects and look at the ideal performance for EVM or ACPR, or I can actually put the interconnects in, which is eventually what we're going to work up to in this video series, and I can look at the effect of these components, linear and nonlinear components, as well as my interconnects. Well, that's it for this installment of PCB layout and system level simulation. If you have more information if you'd like more information about this modeling technique, or you'd like more information about Microwave Office, the AWR design environment, or VSS, there's plenty of information on the website, or you can contact your AWR sales professional.